Hey, hi, welcome to the class. So today's topic is random variables. So we'll talk in detail about what is random variable and what is the meaning of PDF of a random variable, probability density function of a random variable, and cumulative distribution function of a random variable. So we'll talk all of them about all of them in detail. So first let me talk about random variable. So first of all, let us understand what is random variable. So from the meaning itself, we can understand because number of students in the class is 50, whose values are not deterministic or non-deterministic. Whenever anybody uses this word random, you can understand it as non-deterministic. Non-deterministic means not able to determine those values, not able to tell those values exactly. So that is the meaning. So let us come to the mathematical meaning of random variable. So random, what is the mathematical definition of random variable? A random variable is a function of, is a function mapped onto some real numbers, right? Now let us understand this further. Now what is the meaning of this? So this language we already know, right? So what is the meaning of this? It is f of a is equal to 1, f of b is equal to 2, similarly t is equal to 2. Similarly here if you want to write, it is y of h is equal to, y is a random variable which is a function of the sample space. So one of the sample space element if you substitute as input, so the random variable value will be 11. Similarly y of tail is equal to 21. Now if I ask you, what is the probability that random variable values, random takes the values 1 and 2 here. So what is the probability that x equal to 1? It is equal to same as, how did we get this 1 value? X equal to 1 we got from because of the mapping from head to 1. So since head is of head, same probability will be mapped onto 1 also. So probability of x equal to 1 is same as probability of getting a head, which is equal to half. Based on our mapping, the probabilities also will get mapped accordingly. Similarly, probability of x equal to 2, the random variable value, take x square. Right. So instead of writing each and every element, I am writing generally like this. This is the equation that is being satisfied here, or this is the function. This is the function. This is in mapping manner. This is in the equation manner. So x of 1 equal to 1 square, x of 2 equal to 2 square, x of 3 equal to 3 square, and so on you can write. Instead of writing all of them, I am writing it simply like this. Fine. So this is another example. Right. Let me give you one more example for random variable. Let me take a temperature experiment. So let's say I'm measuring temperature in some place, let's say Bangalore, or you can analyze in the same for your own place. Let's say I'm analyzing temperature in Bangalore. Temperature in Bangalore definitely is random in nature, so every day it will not be same, right? So let me assume the sample space. I have to assume sample space. Sample space means all the possible values of the experiment, all the possible outcomes of experiment, we call it as sample space. So can you tell me what are the all possible values of temperatures in Bangalore? It is, for example, let me assume that the minimum possible temperature in Bangalore is 10 to 35 degrees. For example, temperature in Bangalore is 10 and the maximum is 35. Let us assume. So I'm assuming this is the sample space of temperatures in Bangalore. First, yes, definitely I can deal with these numbers. I can define whatever is the sample space numbers, I can define the same numbers as random variable. X of s equal to s. You can define like this. So then there is no need of defining separately a random variable, right? Okay. So here, if you are happy with these numbers, yes, you can use the same numbers itself as the random variable, which means you can assume the definition is like this. Or else if you are not happy with these numbers, then you may have to deal with different numbers. So what would be the reason? Define it according to your convenience. Here, what is my convenience? Here, my convenience is dealing with the degrees Kelvin square. Instead of degree centigrade, I want to deal with degree Kelvin square. Since that is my convenience, what I'm doing is I'm defining a random variable in such a manner that every degree centigrade value will be mapped onto degree Kelvin value, which is 273 plus 10 is 283. Similarly, all the other values also can be mapped in similar manner. 35 degrees centigrade can be mapped onto 35 plus 273 is 308 degree Kelvin. Like this, remaining values also can be mapped. Here, according to my convenience, I have defined the random variable. Now, the random variable takes values 283 to 308 with non-zero probability. 283 to 308 values, random variable takes with non-zero probability, whereas the remaining values it takes with zero probability. So, these are the three examples. So, if you observe in the previous two cases, sample space is discrete, and hence random variable is also discrete. Similarly, in the second example also, sample space is discrete, so random variable is also discrete. Whereas in the third case, sample space is continuous, so random variable is also a continuous random variable because it takes continuous values. There are infinite values possible from 283 to 308. Since there are infinite possible values, we call it as continuous random variable. Whereas the previous two defined random variables are discrete random variables. Fine. So you can also define this random variable in this manner also. Random variable. Random variable is a function of sample space, whereas these functions are functions of random variable. So what does these functions convey us? These functions have the information of probabilities. So the information of probabilities, what probabilities the random variable will have. The random variable takes values, these particular values, and what is the probability that random variable takes 283 to 308. All these information will be there in PDF. PDF and CDF will have same information only, but arranged in a different format. So PDF, as the name says, probability density function. So it is a function of probabilities. It is a function which can show us the probabilities for each and every value of random variable. Right. So let us take some different experiments and let us plot it. So for example, die experiment. For die experiment, let's say I have defined a random variable like this. Random variable is x. Head and tail, we are mapping it onto 1 and 2. Now let us plot the PDF. PDF is a function of random variable. So as a function of x, I am plotting fx of x. So generally the notation for probability density function will be something like this: fx of x. Some people will take it as px of x. Some people will just take it as p of x. The notation can be anything. What is the notation? That is not really important. What is important is whether it is PDF or not. That is important for us. If somebody says PDF, all the properties that we are going to learn, that will be valid. Generally for CDF, they'll generally take the notation as capital Fx of x. This is the general notation. If they follow different notation in the exam, that is also fine. Okay, as long as they say it is cumulative distribution function, we know whatever understanding we have about cumulative distribution function, you are going to apply it. What is the notation they are taking? That's not really important. Okay, so generally the notation followed is this for CDF, and it is small letters that they're going to use for PDF generally. But if they use different notation, that's not wrong. Right? Let us plot the PDF. So x takes values 1 and 2 with non-zero probabilities. Non-zero probability means what is the probability of 1? We know that probability of x equal to 1 is half. And we know that probability of x equal to 2 is also half. So let us plot the probabilities. X equal to 1 probability is half, and y equal to x equal to 2 probability is also half. And what is the probability of remaining values? 1.1, 1.2, 1.3 and so on, 2.1, 2.3, 2.4 and so on. The probabilities of remaining values is how much? It is 0 because there is no mapping here, which means they are not going to happen. They are not happening means the probabilities are going to be 0 for remaining values. X takes all the real numbers, but some values only it takes with non-zero probability. All the remaining values it takes with 0 probability. Right. Now let us understand what is CDF. CDF is also a function of random variable. CDF is also a function of random variable that also consists of the probability information, but in a little different manner. It is not in this format. So PDF will give us what is the probability of the random variable at each and every value of random variable. See this one, at x equal to 1, it is having a probability of half. That information is there. X equal to 2, what is the probability? That is there. So probability density function will tell you exactly what every value of random variable, how much is the probability. That information will be given by probability density function. Whereas cumulative distribution function The same information it will give you, but in a different format. How? So let us understand this. Cumulative. Cumulative means accumulative. Try to understand this. Accumulative. Accumulative. So what is the meaning of accumulative? Accumulated, which means whatever the past values, that it is accumulating them and it is keeping it. So cumulative distribution function means it is a function which shows us at every point whatever value it shows, it is nothing but it is a accumulation of all the past and present probabilities. This function, whatever the CDF shows, fx of x, whatever probabilities that the CDF shows, that is nothing but the accumulation of past probabilities. So I'll just give you addition of probabilities of all the values possible for random variable also should result in 1. You should write the equation much more clearly. Fx of x equal to 0 for x less than 283 and it is equal to 0 for x greater than 308, right? So there are 3 equations for this. So let me deal with this function. Let me do this integration in 3 different regions. So first let me do it for x less than 283. For x less than 283, integration from minus infinity to x. What is this value? X value is less than 283, which means you are integrating from minus infinity to a value less than 283. So the area is going to become 0 only. Because this function value, fx of x value is 0 when x is less than 283. So this is integration from minus infinity to x, 0 dx, which is equal to 0. But when x is between 283 and 308, then what happens? Same equation, so but I'm going to write it as minus infinity to 283. I'm going to divide the limits, and 283 to x and fx of x dx. 283 to x means x is a value between these two. In this range, what is the equation of fx of x? It is 1 by 25 dx. In this equation, I'm substituting 1 by 25. For this range of values, it is 0 dx, because for x less than 283, it is 0. So I'm dividing the limits minus infinity to x as minus infinity to 283 and 283 to x. Because if you want to substitute the equations, you have to substitute based on the limits only. So which is equal to, so this is equal to, this is 0 plus 1 by 25 into x. So if you substitute the limits, it becomes x minus 283. So this is for this range of values. And it is equal to, for x greater than 308, what happens? So same limits, minus infinity to x, but x is a value which is greater than 200. So let me divide the limits into minus infinity to 283 plus integration from 283 to 308 plus integration from 308 to x. Because x is a value greater than 308, I am dividing into 3 limits, because if I want to substitute the equation, I have to divide into limits like this. So in this region, PDF value is 0, and in this region the PDF value is 1 by 25 dx, and in this region the value is the PDF value is 0 again. So if you integrate it, so it is 1 by 25 into x. If you substitute the limits, it is become 25, which is equal to 1. Yes, that is what we want finally, right? So fx of x, finally if you write the answer, it is equal to 0 for x less than 283, and it is equal to 1 by 25 into x minus 283 for 283 less than x less than 308, and it is equal to 1 for x greater than 308. Yes, finally we got the CDF. So let us plot it. It is 0 till 283, and from 283 to 308 it is a straight line, where at 283 it is becomes 0, and then it goes on increasing like this till 308, and at 308 it becomes 1. See this one, 308 minus 283 is 25 by 25 is 1, and it will stay constant at 1. So this is how the PDF. So for any function you can do in the similar manner. So whatever procedure I have taken, same procedure you can take for some other functions also. Right. So finally, let us quickly write what we have understood in terms of properties. Let us write the properties of PDF and properties of CDF. First property. What is the first property? So probability ranges of PDF. So we have to write in two different sections. So this I'm going to divide into two parts. So PDF properties I'm going to divide into two parts. For discrete separately I'll write, and for continuous function I'll write it separately. So let me take the notation for a discrete function. PDF for discrete function as px of x, and for continuous function I'm taking the notation as fx of x. So you can take the same notation, but just to show the difference I'm taking it like this. CDF, let us take the same notation, which is capital Fx of x. Now let us write the first property. The first property is same properties I'm repeating here in terms of PDFs and CDF. So P of x value, what is that value? What is this value? It is always definitely less than or equal to 0, and less than or equal to 1, and greater than or equal to 0. Same property of probability we are copying here. But for continuous function, what we can do, what we can say is, we can only say that it is greater than or equal to 0, but we cannot assure that it is less than or equal to 1. Why is that? Let us take an example and show. Let me take an example. For example, I'm talking about a PDF, and the PDF takes values from -1/4 to +1/4. And I'm saying this is valid PDF. If it is valid PDF, the area should be 1. So width is half, so height should be 2 units, then only the area will be 1. Yes, is it correct? Yes, it is correct. Because you might think that, okay, at 0, what is the probability at 0? You might think that it is 2. No, probability can never be greater than 1. So whenever somebody asks you probability at a particular value, you understand like this. You understand it as 0 minus less than x less than 0 plus. Don't understand the value of the function for continuous PDF only. For discrete PDF, whatever value is visible, that itself is the probability. But for continuous function, whatever value is visible, that is not probability. That is just the function.